Alright, I want to work through problem 10.68. This is the problem where we have a pendulum swinging from the ceiling. So that's a mass M, on the end of a string, length L. And in this problem, it swings down from some initial starting position, 0, to some point right below the anchor, point 1. And then what happens is there's a button here that causes the string to wrap around that point. And so when it does so, it kind of does this. And so point 2 here is at the very top. And the question in this problem is, how high, or what angle, that's very specifically, what angle do we have to start the pendulum at so that when it gets to point 2, it's just got enough kinetic energy to just make it around without the rope going slack. And so what I want to do is actually want to work backwards from the ending point to the beginning, because I think that actually helps us to organize our thoughts. Because if we do a free body diagram at point 2, all right, we get tension acting downward, we get gravity acting downward. And so if I look at Newton's second law in the radial direction, I get F net in the radial direction is ma in the radial, which is mv squared over r. But the condition that it just has enough kinetic energy to make it just all the way around without the tension going slack is that at the top, the tension just goes to 0, which means that the only force acting in the radial direction is Fg, but I'm still in circular motion. Okay. All right, and so mg is mv squared over r. M's cancel. And so I get v squared is equal to g times r. But the radius of this circle, we're told that this is L over 3. So the radius of this circle, g L over 3. Okay, so we're going to keep that in mind. Okay. And so now this is just a couple of energy conservation steps. So the only forces that do work to change the kinetic energy, well, it happens to be gravity. Tension doesn't do any work. Okay, so I'm going to write that down. Tension does no work because all throughout the process the tension is perpendicular to the displacement delta r. All right. So it does no work. And so what we're going to do is we're going to do 2 energy conservation steps. The first energy conservation step is going from point 1 to point 2. And because no non-conservative forces do work, the change in the potential energy plus the change in the kinetic energy is 0. U final minus U initial plus kinetic energy final minus kinetic energy initial is 0. Okay. Well, what I'm going to do, going back to our original diagram here, is I'm going to set the very, very bottom to be 0. That makes the most sense, actually, in this problem, I think. Okay. Which means that the initial potential energy goes to 0. The initial kinetic energy is not 0, nor is the final kinetic energy. But we can say, well, the final potential energy is m times g times 2 L over 3. That's the final height that it ends up at. Plus kinetic energy final, well, that's 1/2 m the speed at point 2 squared minus 1/2 m v at point 1 squared, and that equals 0. But we know what that is. We know that v2 squared is gl over 3. So I can combine a couple of terms here. I'm going to I'm going to combine, I'm going to bring this, the kinetic energy to the other side, 1/2 mv1 squared. And so when I combine these things, so I have mg2l over 3 plus mgl over 2 times 3. And so I get 2/3 here, I get 1/6 here, but 2/3 is 4/6. So I get mgl, and I get 5/6 coming out front, and that's 1/2 mv1 squared. And I'm going to leave it just like that. Okay. Because the second thing that I'm going to look at is the kinetic energy, or I'm going to look at the energy change from point 0 to point 1. And again, no non-conservative forces do work. So delta U plus delta KE is 0. U final, minus U initial plus kinetic energy final minus kinetic energy initial is 0. Well, if I'm starting at point 0, my final potential energy, I'm at the bottom, so that's 0. My kinetic energy initial is 0 because I'm starting from rest. Okay. And this is the kinetic energy at point 1, which I've already found. I know from this part that kinetic energy at point 1 is 5/6 mgl. 5/6 mgl. And so I can rearrange this. My initial potential energy is 5/6 mgl. Or in other words, my initial potential energy has to be this in order to give me the correct speed at the very, very end to just get around that arc. Just get around the top point without the tension going slack. Okay. Well, let's take a look at this. So I'm going to redraw that diagram. So this is my diagram here. So this is a length L, goes down. This whole thing is length L, and this is some angle theta. Right. And so the height at the beginning, we're going to call it height H. So that's the height above the 0. And the best way to do this is actually to also define this as some x, because x plus h has to be L. And x I can find from this triangle there. So I have the adjacent side here. So I have L cosine theta plus h, what I'm interested in, is L. Or h is equal to L times 1 minus cosine of theta. And so the initial potential energy is mgh, which is mgl 1 minus cosine theta. Or, put it together with our energy conservation, I get mgl 1 minus cosine theta is equal to 5/6 mgl. mg and L all cancel. And so if I rearrange this thing, I get 1 minus cosine theta is equal to 5/6. Bring the 5/6 over here, bring the cosine over here, and I get cosine of theta is equal to 1/6. Or theta is the arc cosine of 1/6, which turns out to be about 80.4 degrees. I better plug that in. The inverse cosine of 1/6 gives me, about 80.4 degrees. Okay, so you have to pull it back quite a ways, but this problem is nothing more than just a bunch of energy conservation.